Cyrus.
And I'm James.
So we split this project into two parts. Luke did most of the objectives with the two interfaces and combined them into one interface. And James and I, we split up the exploratory data analysis parts and model building. Yeah.
So the first tasks we did were the literature research tasks. So the first one, where we'll describe the process of the pressure transducer calibration using a deadweight test bed. This generates precise pressure by placing calibrated weights on a piston of known area, given by the equation P equals F over A, where F is the weight of the weights, and A is the area of the piston. The process is as such. One, we prepare by cleaning the apparatus and then filling with proper fluid and getting all that prepared. Second, we do the zero check, where we tare the weights and make sure it all reads out as zero. Then apply the known weights onto the piston and spin it gently until it floats freely and stabilizes. Then, four, we record the output and measure and note the transducer's output corresponding to the applied known pressure. Then, we repeat across the range to make sure that we have precise numbers and accurate numbers. Then we calculate error and adjust, comparing measured values to true pressures, calculate errors, and adjust the transducer as needed. 7. We document the results, record all readings, corrections, and uncertainties to complete the report. For the second part of the task, we find that a calibration model is valuable because it turns raw voltage readings from a pressure transducer into meaningful pressure values with units. Instead of guessing what the voltage is, the model uses measured data to create an equation that estimates the applied pressure. It also helps describe the uncertainty in the estimate so the user knows how reliable the pressure reading is.
For the exploratory data analysis part, this basically it finds a relationship between the columns. So the first column is the test ID. So there's like nine trials, and then the second column is the true pressure. And the third column is the analog gauge pressure reading, and then the fourth column is the pressure transducer's voltage output. Right. So this make model function, it finds a curve-fitted line between certain columns, or whatever the user's columns input is. And then it also calculates error between the actual values and the predicted values, and then calculates the uncertainty level. And then this plot with fit function, basically plots the line given by the make model function, and does all the graph stuff. So here, for the first relationship, we have the pressure, the true pressure on the x, and the analog pressure on the y-axis. And then we found the y equals mx plus b formula. So they're almost like 1-to-1 with a very small, almost 1, almost m equals 1, and then a very small b value. And then it also returns the error or uncertainty level. It's like plus or minus 2.33. And then below this, you have the analog, and then the voltage relationship, and then you've got their formula for it, and then the uncertainty level. And then we also got the true pressure and the voltage relationship. There's stuff for here. Okay.
All right. So for our first two tasks, which go together for the model building, we have our calibration plots. So what the function does is it takes two columns of data, takes all the x values and all the y values, draws a scatter plot of the data points, then fits a straight line through them. So our best fit line. Each line specifically is our voltage to true pressure, shows how voltage relates to the real pressure, where we have our approximate confidence and our uncertainty, and then our little plot, which has our blue data points and our red line of best fit. The same for our second plot, which is our analog gauge to true pressure, And our third plot, our voltage to analog gauge. Key point of this is it takes two columns and the plot points and then draws a best fit line. That's all this program does, which gives us a visual representation of our areas of data. So for our third model building task, what's happening is we're using the make model function, which looks at past data, finds a line of best fit, slope, and intercept, and also calculates the uncertainty in that model. The second make model function does the same thing, but for voltage and analog gauge. However, this one requires a user input of the sensor voltage. So, say we use a sensor voltage of 2. It gives us our estimated true pressure, our uncertainty, plus or minus 0.87, our anticipated analog reading, and our confidence level. So, next, what we have for task 4 is the code here is building a model from our analog gauge and then gives it true pressure. So our input value is 64, which is hard-coded. We then convert that into estimated real pressure, and then it prints our original gauge value, our estimated pressure, true pressure, prints the uncertainty range, and then the 95% confidence level, which is fixed. A similar thing happens for task 5, but instead here, voltage to true pressure, and then it converts that to estimated pressure due to the 1.4320 volts, and then it outputs our input voltage, our estimated pressure, our uncertainty from the model, and our fixed 95% confidence level. Task 6, however, is table processing using multiple unknown voltages. So our first one is it builds a model, same as before, voltage to true pressure. But then it creates a table using test values and then sensor voltage values, which is a table with 5 rows. Each row has, like I said, the test ID and the voltage value. It then applies the formula to every row by taking each voltage value multiplied by M true, add B true, and then store in a new column. And it does these automatically and at the same time. Then adds uncertainty, adds a confidence label, and gives us a final output of the test ID, voltage, estimated pressure, uncertainty, and confidence level, all in one table.
Where's some all
Right, this function takes the data or creates a data frame out of the data in the CSV file, and then it uses that information to create functions for the lines of best fit, comparing the true pressure and the analog pressure to the voltage, so that it can predict what future analog or true pressures may be for new voltages. And then it down here calculates the estimated uncertainty, the error, using standard deviation from the NumPy library. The interface is this whole while loop. If you go ahead and use it, you have 2 options. You can, one, estimate new pressures from a voltage. So if we were to enter 2, we would get our estimated voltage at...
I gotta press one first. I'll just.
Oh, okay. I see. Misclick there. So we didn't take this part back out the video.
Making.
Okay. Gotcha. So now you hit 1, you choose option 1, you enter your voltage, and it'll give us our estimated true pressure, uncertainty, and analog right here. And then we have the second option, which is to add a new observation. That means that we are adding new data to the data frame that will affect the line of best fit for the future. So if you add a lot of new observations, eventually your line of best fit will change and you will have new estimations for voltages. So if we were to add a test ID and then we gave it different pressures and voltage, then it will go ahead and add that to the CSV file. So if we close and reopen the CSV file and scroll all the way down, right here at the bottom, number 110, we have 11, 124, 128, 123, which is what I just entered. That's pretty much it. You got anything else?
That's it. Okay, thank you.